Welcome to the Rare Earth Exchanges podcast, where power, politics, and the world's most coveted materials collide. Rare earth elements power the backbone of tomorrow's most critical technologies. With China dominating global production, the U.S. and its allies must align strategically to ensure a stable future. This urgency prompted tech entrepreneurs Daniel O'Connor and Dustin Olson to launch Rare Earth Exchanges, a news and insight platform built to equip stakeholders and decision makers with the tools and intelligence needed to reduce dependency and build prosperous resilience. Let's get into it.
Hey everyone, welcome to the Rare Earth Exchanges podcast. Today we are joined by two amazing experts from Koch Modular. We've got Chris and Brandon, our engineers, senior engineers, correct? I think those are your titles. Yeah, sure. Awesome. You guys have quite the experience, and with what your company is doing, I would love just to kick the show off by hearing what a high level overview is of Koch Modular, some of your core philosophies, and then also how you guys are going to be contributing to the rare earth elements space. And that either one, Chris or Brandon, if you guys want to kick it off.
Chris, you want to go ahead and then I'll piggyback off you?
Sure. So I'm Chris Wrench. I'm the process development manager at Koch Modular Process Systems. We're a modular EPC, which means we do engineer, procurement, and construction of chemical process facilities. And we've been providing modular systems for a range of businesses over the past several decades. The rare earth space is one that lends itself towards liquid extraction technology, and that is one of our core capabilities. That is what's considered a mass transfer technology, and liquid extraction plus distillation together being two of the major mass transfer methodologies used in chemical engineering process design. So we've deployed those technologies any number of times across a variety of businesses. And now that the demand for rare earths has increased substantially domestically, we see an opportunity to deploy our technology into that space as well. And me personally, by background, before I hand it over to Brendan, I've been working in the chemical engineering space, either in design or production in hydrocarbons, lithium-ion batteries, biochemistry, and a handful of other processes over the last 20 years. So this continues to be my desire and passion to see chemical process technology developed and deployed into new and novel spaces.
And I'm Brendan Cross, principal extraction engineer at Koch Modular. I have a similar amount of experience to Chris as to I've been at Koch Modular for about 20 years now. I have a bachelor's in chemical engineering, and we've, as a company, have been working in liquid extraction or solvent extraction for about 40 years. And we're completely based in the U.S. We test, develop, design, and build processes completely in the United States. We're completely kind of domestically grounded, and we think we have the technology that would be a great fit for developing these types of processes.
Excellent. Dustin, do you want to maybe lead? I have some questions, but maybe just lead off based on, the questions that we've developed.
With your guys' extensive background, can you give just some of our listeners some extra context who may not be the chemists? Can you use some of the fundamental techniques or challenges with rare earth separations? And then why is it so difficult to separate?
So rare earths are so difficult to separate from one another because they're so similar in nature. So generally speaking, it's really difficult to separate a molecule or element from one another, the more identical they are to one another. And when you're looking at rare earths, you're basically looking at the periodic table. If you go down to the bottom two rows, the one that sits on top of the bottom two rows is all those rare earths. And they're distinct from one another basically by one atomic mass. So that makes them extremely challenging to separate from one another. And solvent extraction is a type of technique that's been used to separate them. Historically, solvent extraction has been used for metal separation, say things like nickel, copper, cobalt, since the 40s and 50s. So it's been demonstrated and vetted at industrial scale and is economical. And because of that, it's been used for rare earths as well.
I was going to add in that I think we're excited about your company looking at this space, moving in this space, because there's going to be a need for larger players that have the scale, the infrastructure to do this economically. Okay. And it's a national security matter, right? It's beyond just a market need. You all know the conditions today are such that China has monopoly. And so we need, well-capitalized large companies that can commit to do this at scale. Have you all, before we get into some other questions, sort of studied over in China? There's a few operations. I'm assuming you all have studied sort of what they're doing and figuring out even more innovative, advanced way of evolving. Like the technology, can you drill into it a little bit more? Is it developed in-house? Did you partner at a high level? How did you evolve this technology?
So traditionally, these types of rare earth separation processes are done using something called mixer settlers. That's kind of the classic solvent extraction technology. So a way to kind of envision those is imagine you have a mixing tank, and then right next to it, you have a settling tank. And the way solvent extraction generally works is that you have a molecule, or in this case, rare earth elements, in an aqueous or water solution, and you're trying to pull those out into an organic phase, which is the solvent in solvent extraction. So you mix them together in a mixing chamber, allow them to flow into a settling chamber where the two phases separate, and you've extracted some of those rare earths into the organic phase. The way this works at scale is because it's such a difficult separation. Something like copper, you may only need 3 to 5 mixer settlers, kind of lay it out horizontally against one another.
Right.
Like rare earths, you require hundreds of them. And that takes up a lot of floor space, takes up a lot of volume. So you're going to have a lot of solvent held up in the system, which is kind of a huge CapEx hit right off the bat. And then you have a lot of valuable product. The actual rare earths are held up in the system too, just because there's so much mass and volume associated with these types of systems.
Right.
So just to maybe envision this a little bit, a mixer settler, a small one might be the size of a household refrigerator laid on its side, and a larger industrial production scale one might be the size of a fifth wheel camper trailer pulled behind a pickup truck. And that would represent one mixer settler stage. You might need a cascade of 30 of these to purify one rare earth element. And there's about 17 rare earth elements. Multiply whatever 17 times 30 is. We're talking multiple hundreds of mixer settlers laid out side by side. And that's a large volume of liquid that when you first turn it on, it has no rare earths in it. And as you continue to feed the process over time, the concentrations build up or equilibrate. And once they reach their equilibrium concentrations, that's when you're in full production mode. But that time delay to bring a large cascade of mixer settlers online could be measured in months, not days or hours. And that's one of the reasons we like our extraction technology offered by Koch Modular. The Scheibel column is a tall, skinny column by comparison to these large rectangular vessels. And a taller, skinnier column has less liquid inventory, but a similar production rate. So it doesn't take nearly as long to equilibrate and bring it to production mode.
Fascinating. That's really fascinating. And this is something that, again, is developed within the company. And it's interesting because a lot of folks, laypersons, don't realize that rare earth element processing is more sort of like petrochemicals than it is sort of traditional mining, as we learned, right? So it makes total sense that the company is moving into this markets. I mean, as you look at, okay, so we have the Koch Modular approach. There's a few other initiatives unfolding in the United States. I'm sure you all have sort of scanned the market. And are there other instances that you know of that are coming up with novel approaches? What does that market look like so far? Is there any other group that could potentially operate at your scale, producing, building at your scale that is out there? Or do you all feel very confident that, sort of you're going to be ahead of the point of the arrow?
Well, to be clear, we're sort of agnostic to which source of material enters an extraction column. We would help and work with any client or developing tech company that wished to deploy liquid extraction to purify and separate rare earths. That said, yes, I'm aware as a process development guy, I'm aware of multiple other technologies that might want to compete or be an alternative to a liquid extraction system. Most of the time, the criticism of liquid extraction is it uses toxic chemicals or flammable solvents. And this is true. And it was more of a detriment 30, 40, 50 years ago when they didn't put lids or roofs on the mixer settlers. They were open baths emitting vapors to the environment. Nowadays, they're totally enclosed and you can put spill catchment basins around them. So the risk that you'll lose the chemical inventory to the environment is quite minimal. So that's the major criticism here. The advantage of liquid extraction is it's been proven. It was developed in the 60s and 70s, and it sort of took over the market in the 70s. It displaced all previous technologies that used to exist to purify rare earths. I'm not aware of anyone who industrially practices fractional crystallization anywhere. There are still some niche applications for small volumes where ion exchange is used to get to very high purities, or some sort of chromatographic deployment. The disadvantage of using ion exchange and chromatography is you end up with very, very dilute solutions of the rare earths. So the aqueous or the water-based solution that enters the process is about 100 times more concentrated in rare earths when you're doing it by liquid extraction than it is by chromatography. Which
Makes sense. Makes sense. Chris, I had a question, just context, history. This sort of methodology of separation, I believe this was invented here and then outsourced to China. Is that correct?
Sorry, I know the name of the gentleman who invented it. His name is Fisher. 60s and 70s was the time era. And I don't know if that was a United States invention or not.
Okay. That's helpful. Dustin, you want to ask any questions?
Yeah. So I think too, within the industry, those who are new to the time it takes for processing to happen, you said it takes months for the solvent extraction to work to get rare earths out of the solvent. Is that correct?
Using mixer settlers, yes, because there's just so much volume there. To kind of add a little bit more color to what Chris was describing before with the Scheibel column, you could almost envision a single Scheibel column as containing 10 to 15 mixer settlers. So you're doing all of this mixing inside the column, and there's essentially one settling section at the top or bottom of the Scheibel column. So that greatly reduces the amount of volume required for a single extraction column in comparison to 10 to 15 mixer settlers. And it also makes them environmentally a little bit more friendly because you're just going to have less of that solvent and those chemicals held up within the system.
Wow. See, it never would have occurred to me that it would take so much time for a process to happen, which just further adds there's nothing quick about procuring rare earths. You guys also supply the machinery, the systems for other companies to do this. What is the turnaround time? Should somebody want to build out their own facility? How much time is required to bring a new facility online?
Typically, we would encourage a engineering and design timeline of around 3 months. And then following that, we would be looking at, depending on the size of the equipment, 10 to 12 months from the time the hardware is ordered to the time it's showing up at the site. And that's moving pretty quickly, which I think is the answer folks are looking for. They want to know the fastest timeline you can get to when you're deploying a rare earth separation system. That doesn't confer the entire advantage, though, for building a modular system. It is possible when we're laying down modules in a shop, everything's built in the horizontal in one of our shops. The on-sites can be working on the concrete foundation. They can be building the control room. They can be building out all the utilities. And so you have a site that's being constructed, and it can be in a very clandestine location. You can be right next to a mineral deposit or someplace that doesn't have a lot of craft labor available. And then the trucks roll in with our modular hardware. All the piping's done, all the instruments are done, all the installation's on. So everything goes together like a big kit in the field then. And that minimizes the amount of people you had to bring in to do that construction and speeds up the schedule considerably.
I think that's amazing. To have one of these set up in about a year is absolutely phenomenal. That's on that note, and I don't want you both to share any proprietary information, but are there any discussions happening right now for Koch Modular to build facilities?
I could say we're very active in the space and talking to multiple potential clients for building out these types of systems. And I think another advantage of working with us that I'd like to mention is that the Scheibel technology is our proprietary technology. No one else builds it. We're a company of essentially chemical engineers. So we would start ideally with a rare earth concentrate from a specific site, go into our lab. We have a pilot plant, which is really an R&D solvent extraction facility in Houston, Texas. We do some bench scale tests to get all the data that we need so we can kind of come up with a preliminary engineering design for the process and also a pilot test design. And we would pilot test the entire process or everything that we need to using pilot scale Scheibel columns. So those are pretty small. They're 3-inch in diameter. They're made of glass shells, so you could see everything that's going on. And then coming out of a pilot test campaign for a rare earth process, our systems being delivered to the site would have a process performance guarantee. So that gives our customers a lot of confidence in our systems that they'll work as designed because we provide that process performance guarantee, and they see everything that's taken place in pilot testing in our solvent extraction pilot plant in Houston.
That makes total sense. Very powerful, very powerful. Again, from our standpoint, we report on the dire nature of where we're at from security and supply chain perspectives. So knowing that your company has this infrastructure and the wherewithal and the technology to build and deliver something like this at that amount of speed with the agility that you offer is something else. Actually, it's extremely valuable.
Yeah.
So go ahead, Chris.
I would say we're not yet, well, we don't wish to be, but we're not exclusive to any particular company that wants to do rare earth separations. And I've kind of been a little bit surprised how few inquiries have come in. Actually, we're actively marketing the technology. We think that the solvent extraction approach is the least risky, most proven, and probably fastest to deploy, whether you're starting from bastanite or monzonite or coal fly ash and you're trying any of those approaches, you're going to separate all the silica and alumina and arrive at a mixed rare earth concentrate. And everyone's got the same problem at that stage. How, when you've got all 17 rare earths mixed together, it's at 90% concentration, but it's all one mixture. How do you separate those and tease them apart into their individual elemental baskets? And that's where the Scheibel column and solvent extraction can be rapidly deployed. Each of those ores has a different proportion and ratio of the different rare earths. So you really do need to pilot test each one individually to establish the right liquid ratios and the right size equipment to go after each of those elements. There's no one size fits all solution in this space.
Yeah. And it's important, Chris, what you brought up, that it's still, it's still very early days if you really think about it. That this problem has just sort of, ensued with no real critical calling out of the issue until recently, until President Trump was elected and there was the Liberation Day effort and but either way, I think now it's becoming on people's radar. So I think from a business development perspective, it's still early days. It surprises us how much of the media, even those media purporting to have experts reporting on this topic, it surprises us how much they miss as to the nuance and details of this industry. So I think part of the issue is it's still very early on. There's obviously a couple prominent efforts that are funded by the U.S. government, DoD, what have you. So obviously, from a business development perspective, it's critical to be inserted into those discussions and figuring out, speaking with a few different emerging, I would call it spheres of interest or clusters of activity, how to contribute to that value chain, I think, unfolding right now. What we see, we did our homework on you all, and we, again, like the scale. We like the pedigree. We like the expertise and the amount of talent, wherewithal, financially. And so we think that it's a very important offering that you all are introducing to the market. And again, Chris, I think Chris and Brendan, I think it's still early, right? So it's very much a business development effort, I think, in knocking on doors and getting people to understand, including the federal government, why such an approach will be vital at scale if we really want to be independent, have a resilient supply chain. Does that make sense to you both?
Absolutely.
So I guess, I don't want to mention specific companies here. I want to keep it pretty high level. But let's just say, we know that there's one big active mine in the United States that recently received funding from the U.S. government to rapidly accelerate their effort to contribute to an independent supply chain. That's one sort of center of activity. There's a few other efforts where government funding has been involved. So I would imagine those clusters of activity would be of high interest for you all.
Yes, that is a true statement. We would love to see our technology deployed at a domestic mine for purification.
Yes, and there's several mines that are actively I can share with you all, actively involved or in the process, early stage of developing the mine, bringing it towards construction.
Mm-hmm.
Also internationally. Now, remember, from our standpoint, obviously we're a Salt Lake City based company and, we have our biases towards US based activity. But for us, ex China means outside of China. And so on one level, we don't care if it's a US or Brazil or Europe, we want it outside of China because that's the biggest national security threat right now. Okay. So we are aware of situations where capital is flowing into places in Brazil, places in the continent of Africa, where your services and your technology could be very useful. Have you been talking to overseas?
And we're certainly aware of deposits outside of China where our technology could be used to purify rare earths.
Well, an example is Malaysia. Malaysia is very clear. Obviously, they have the Linus facility, but they have other mines and they have an interest in ultimately adding more value, keeping the value in that country. And there's some big players that are looking at processing technology, separation processing technology. There's some very interesting initiatives happening in both Australia and South America, like Brazil, Canada, even countries in Africa that are interested, like Nigeria, which has refining know-how from all the oil industry there. So I see definitely locations around the world that could benefit from this modular approach, I think.
Dan, what I would say there too, as a company, though we are US based, we've supplied large modular systems across the globe. So APAC, Europe, South America, we've done all of that. And there's also nothing preventing us from providing some of our pilot scale equipment to a company that was, say, in Australia or Malaysia, something like that, where they could use our technology with guidance from us remotely, or possibly we go out there to help them. And then we would just take all of that data to design a large modular system for separating rare earths.
And that's great to know. Oh, go ahead, Chris.
And as much as I like the analogy of a modular package to a shipping container, I often point out to folks who are putting inquiries into our company that our modular systems are actually significantly larger than a shipping container. A shipping container is 40 or 53 feet long and 9 feet wide, roughly, and our modular frame can be up to 80 feet long and 14 feet wide. It's right at the on-road dimensions that don't cause too much difficulty getting around and over bridges and under tunnels in the United States. So we can drive a module anywhere in the 48 contiguous United States. We can put it on barges, and indeed we have put ships to do international shipments. There's modules operating all throughout the Caribbean that have arrived at those islands by boat. So we can and have done it. It's just a matter of building to the local construction standards and codes.
Yeah, and a question I sometimes have, because I know you're part of a much bigger corporation. We know of some entrepreneurial scenarios where individuals or groups have serious potential, for example, mining claims and discussions with governments. And I could see your offering fitting nicely into that as a holistic package. But, again, it would take some business development and due diligence on your part to, figure out if it makes sense for you. I think as part of the rare earth exchanges offering that we're doing, we're happy to make, introductions and such, because again, our mission is to accelerate the ex-China rare earth supply chain, and by extension, even critical minerals, just because it's important for our national security. Let's talk a little bit about heavy rare earths. So if we look at military or defense applications, there's certain heavy rare earth elements that are completely monopolized by China at this point, 100%, pretty much. There's a little, Linus has produced a little heavy rare earths. If you look at our heavy rare earth rankings, we include ex-China assets that are out there, but ultimately China, Laos, Myanmar, they pretty much control that space. Is there any differences when you're using your technology separating these? I've heard by some groups in Asia that it may be harder or more difficult to separate the heavy rare earths. Is that true from your perspective, or does it make a difference?
So Heavy rare earths are coincidentally the first rare earths extracted in a liquid extraction system. So when we do solvent extraction, if you could only choose one, it would be the first one to come out. It would be lutetium if it's there at significant concentrations.
Mm-hmm.
Struggle that I believe the Mountain Pass mine has in California is it's fairly depleted in the heavy rare earths.
Mm-hmm.
So you need a mine or you need a deposit that's got some reasonably high concentrations. And when I say reasonably high, a 0.5% or 0.1% would be high for a heavy rare earth in a deposit that's, more typically of its rare earth content, 30% cerium, 20% lanthanum. The light rare earths tend to dominate the deposit, and then the heavy end would be negligible sometimes. That said, we can certainly design a system that focused on the heavy slice. We would pull the heavies out and separate the heavies individually and get your terbium, europium pulled out individually and purified to better than 99% purity. That can be done. It's just a question of what your objective is and what your process design. And to that end, the folks who are focused on coal fly ash, they have a simultaneous challenge and advantage. Their challenge is the rare earths are 1/10 to 1/100th the concentration in coal fly ash as they are in naturally occurring deposits. The
Right.
advantage is they tend to be more rich in the heavy rare earths. So if you're going to go and target heavies specifically, there are probably some coal fly ashes that have an advantage there.
That's fascinating, Chris. I didn't know that. And there are a few efforts, as you know, in the United States involved with that. And I think it's, again, I don't, there's national security implications, but I think it's definitely a topic worthy of further exploration just because of what we know about the monopoly that's in place right now. I think, traditionally, you don't need a lot of this stuff for various defense related products, but you need it. And to redesign these systems and these products to not depend on the small amounts of rare earth magnets, for example, is probably years away and expensive. It's fascinating to think about a tailored modular approach for heavy rare earths for defense purposes, right? Is a very intriguing concept.
Yeah, I'm liking it as well, hearing you say it. And all we need is the proper amount of interest from preferably a company that has a deposit, knows how to pull the rock out of the ground and do the ore beneficiation. So it's not suitable to hand us a 2 to 3% fresh out of the ground rock,
Right.
slurry or solid. It's got to be taken up to that, better than 70% total rare earth oxide. And at that point, we can now really do something cool with it.
Yes, understood. Fascinating. Really, really fascinating. So how long has the current modular rare earth solvent technology been available in terms of Koch Modular can build this for companies? A year old, 2 years old? Like, when did you first announce this offering?
Going back to the Scheibel technology itself, which is what we're looking to deploy here, was developed in the 60s, late 50s, early 60s. And those columns have been used for all different types of extraction applications since then. I mean, there's many of them that predate me that are still out running in the US and across the world. So it's a really established technology that's been scaled up from the pilot columns that I mentioned before.
Right.
As a company, we've been building process modules for over 40 years now. And several of those are still out there running too that predate me, and I've been out and visited some of them.
But specifically to the rare earth effort, we've followed the market's interest and we try to become relevant to whatever the current needs are of the industry. 5-10 years ago, there was a lot of focus on biochemistry. 10-15 years ago, there was a lot of focus on silane for solar panels. So our company had offerings in all of those spaces. It's just been in the past year that the extremely loud demand for a rare earth separation technology has prompted us to put together the website and make the commercial offering. And we've put rare earths through our pilot line before. I believe it was back in the late 2000s, I want to say. So it's been a while. And the technology has evolved since then. And the approach we have now that we're ready to take, I think would work better than what we saw 10-15 years ago. So it's the other thing that we've done is we've, I don't know, Brendan touched on it earlier, but we talk about separation factors in liquid extraction. If you were to run your mixture through one mixer settler and it emerges out the other side. By how much have you enriched the thing you're looking for? A factor of 3, a factor of 1.5, a factor of 1.01. These are all sort of enrichment factors that we have seen in liquid-liquid extractions before. The lower that factor is, the closer to 1 it is, the number of settling stages you need blows up geometrically. So you have to be prepared to deploy a lot of liquid-liquid extraction. And this, again, goes back to the advantage of using a Scheibel column. The Scheibel column can probably do the job of 10 to 20 mixer settlers in one vessel. And so we're shrinking the footprint and reducing the capex substantially to get to these purified and especially the heavy rare earths.
Makes sense. Makes sense. And just so the audience knows, so again, the prerequisite for, let's say, a mining partner, they're processing merc to oxides. I mean, they're coming with processed oxide that, like, can you walk us through what does that mine need to have ready for you to go to work to build this and enable whatever group to start separation? Like, what stage in the mining process do they need to be for there to be perfect, ready to go scenario?
Yeah, and I'm not a mining guy, so I'm probably going to say some incorrect things here, but I'll do my best anyway. My understanding is some, if not most, of the Chinese mines do in situ leaching, where they take a lot of ammonium chloride or ammonium sulfate and they spread it on the ground and collect what sort of leaks out the other side, and that will be enriched in rare earths. And they didn't have to excavate much or any of the earth to make that happen. Compared to other facilities, I believe Australia is probably a good example, where you dig up the ore and now you have to soak it or leach it either in a strong caustic solution or a dilute sulfuric acid solution to pull out some of the rare earths. And before you can even do that, you don't want to expose all the sand and silica and other things to those chemicals. That would just increase your chemical consumption. So they do some clever things with size reduction, comminution to break up the rock. Then they expose that to dissolved air flotation systems, where you put a little bit of a soapy molecule in there, like a sodium lignosulfate or byproducts from pulp and paper mills. You squirt that in, it creates bubbles, and the bubbles will preferentially lift either the rare earth bearing or the non-rare earth bearing minerals out. So you do sort of a gravity separation. And this, you get these, unattractive looking foamy sludges coming out. It's a well-established technology, not one I'm familiar with, but by the time you come through 4 or 5 of those processing steps, what you've got is a nice, clean, but still mix of your rare earth elements, but there's not a lot of the other stuff in there anymore. All the sand and alumina and clay has been removed.
Yeah.
That's the stage where we want to be. So
Right.
we sit right in the middle. Someone operates the mine and beneficiates the ore. We sit in the middle and separate the rare earths. And then someone else is going to take those rare earths and put them into a magnet, put them into a fiber optic cable, put them into, some high-tech radar absorbing paint the military needs or something like that. But in the middle, you need someone to unmix the 17 rare earths. And that's what we're trying to do.
Right. And that's really helpful, I think. And I appreciate that, Chris. And also, let me know, from your perspective, do you all also want to talk to the magnet companies or other components assemblies that are more refined downstream product and attack it from that standpoint too, as a go-to-market and, the networking to find the right projects? Is that, I'm just sort of exploring how this show can help you evolve. Is that something you would do too, like conferences and such?
I think a direct introduction to the purchaser of the purified rare earth oxide is probably interesting if they're interested in vertical integration and they're trying to move upstream and sort of control their own destiny with a completely vertically integrated supply chain. Otherwise, we're not a producer, right? We sell the hardware so that a company can sell and market purified rare earth oxides,
Yes.
but that's not going to be our specialty that I can see in the near future.
Understood. But still, that vertical integration, again, let's take the defense and supply chain security as an example, right? Clearly, the federal government has a significant, serious interest in our resilience, right? So there's investments happening. So somebody, would benefit from this approach, putting it in place, having it domestic or at least accessible to domestic, so that we could produce at scale, is how I'm thinking. Who that entity is that would actually, procure the system from Koch Modular, it would depend, right? But it would have to be an integrated scenario, as you said, which makes sense. Is there any other topics you both think are important that we haven't covered?
Maybe just to go back on what Chris was saying about having us taking the upgraded rare earth concentrate. For pilot testing, we don't need much of that material. We don't need much for the bench scale tests that give us the data required for us to do some initial modeling and pilot test campaign design. And then going for the actual pilot test campaign, probably talking something like 10 to 20 pounds of the actual rare earth concentrate. That's enough material for us to test out the Scheibel technology at a pilot scale so we can design the entire process at industrial or commercial scale.
And that's really helpful, Brendan. And on that topic, let's talk pilot. Let's say someone out there that's watching this is interested. Can you walk us through a high level project plan of a pilot? Not the full production, but just the pilot, so that folks out there can understand what they're looking at, like from the start of the project to the end of the project, duration, resources involved, and the key milestones.
So the first thing we'd want to do is we'd want to have a small amount of that rare earth concentrate so we can get the thermodynamic or equilibrium data that we need to do some initial process modeling and calculations that allow us to move on to the pilot test campaign. And for that, we'd want to test out different types of solvents or extractants to find what's most effective for a client's feed material or a rare earth concentrate material and their process goals. I would say that's probably a 4 to 6 week effort for us. And then coming out of that, we do some preliminary engineering and modeling and then move on to a pilot test campaign. And depending on how many products the company is looking to make, if they're looking to separate all 17, it's going to be a longer effort. If they're looking to separate, maybe just do more of a crude split, it's a short effort. For the purpose of what we're discussing here, I envision that as like a 3 to 4 month activity at our pilot plant in Houston.
Okay, so sorry, go ahead, Chris.
And our pilot is staffed with operators to run the equipment around the clock if needed. We have a fantastic analytical chemist and also one of the more expensive pieces of analytical instrumentation that you need to actually take a measurement of the concentrations of your rare earths in an aqueous sample. You need an ICP to do that. It's a pricey piece of hardware. We have that one coming up to speed right now. So go ahead.
ICP, Chris, can you define that again?
Inductively coupled plasma. So if you want to measure how much rare earth is in your aqueous sample, you have to take a little tiny droplet of it and, run it through essentially a lightning bolt and excite all the metals and then watch the flashes of light that come off at different wavelengths. And that's how you measure their concentrations.
Got it. That's exciting. It's really exciting what you all are up to. I can see the potential. I don't want to go into the economics. I think that but at a high level, I would imagine, if someone wants to do a pilot with you, there's a spectrum of business out there involved with these activities, from, larger companies and even government agencies that are somehow involved with contractors, to more entrepreneurial, more bootstrap type of scenarios. Is Koch Modular, let's say, you're working to add value in this emerging nascent market. Do you have the ability to be agile and to tailor the offering to, let's say, more entrepreneurial scenarios where there's maybe, there's capital, but maybe not as capital as if it was some multinational defense contractor? I mean, do you have ways of doing business in an agile entrepreneurial way?
Yeah. In fact, as we speak, I think 6 of the 8 companies I'm personally interfacing with and working with are venture capital backed developing tech companies. Now, we also do business with Fortune 100 chemical companies as well, but we have a long history of successful working relationships with developing tech companies. And we have met directly with their funders, for example, met their timelines. We've cooperated with folks who are working on DOE timelines, who have to deploy technology per the Department of Energy's schedule. So yes, in all regards, yes.
That's excellent. Again, it may not be relevant. There is interest in recycling out there. We've spoken with different companies. One in India, which was actually quite impressive. I think currently today, only about 1% of rare earth downstream output, whether it's magnets or other types of output, are derived from recycled. That's going to change. I know that there's initiatives out there. If you have a recycling paradigm, is a Koch modular approach, is there any relevance in terms of how you interface with that? If this is the wrong question, just tell me. But I'm just curious, in recycled paradigm, is this step not needed, or do you need to go back to this step?
Brendan, I'm curious to hear what you're going to say, but I'll go quickly. Recycling is an even better fit for liquid extraction with a shiable column because your feedstock is already essentially fully concentrated. It may not be at the right ratio. You might have a neodymium praseodymium magnet that you wish to alter the ratio of those two elements, so you need to dissolve them and separate them. But because you're not dealing with all 17 elements, there's already been a preliminary separation done. If you're recycling a samarium magnet or something like that, or a NdPr magnet, the number of processing steps is reduced, the volume of solvent is reduced, the number of columns you need is reduced. And so it's much simpler, in my estimation, to deploy shiable column technology for a recycle process versus 17 virgin rare earth element separations.
Totally agree, Chris. And because of that, you're going to progress through the equilibrium testing and pilot testing much quicker just because there's less unit operations or solvent extraction steps involved.
That's really good to know. I do know from sources that we have that are either associated or on the outside of government, talking with government, but also certain elements in the government itself are very interested in the recycling paradigm because it's sort of disruptive if you think about it, right? I mean, take the heavy rare earths where it's like 50% of the inputs come from Myanmar, where there's a lot of problems. So the more we can sort of bypass all of that, and actually have a circular economy, the better, right? It really makes a lot of sense. This has been fascinating. Really, you guys, really exciting work you're doing. Dustin, any sort of last minute questions that you have for the team, for Chris and Brendan?
My favorite one to ask is, if you were to put everything into perspective, we've talked about an awful lot today for a variety of areas that Koch Modular can fit into. If you put it on the perspective, what would you say?
I'll take a shot at this quick, Chris. But I think our in-house capability, our technology, the fact that our company is pretty much very concentrated in chemical engineers gives us kind of a unique offering to the market where we can develop and build one of these systems domestically very quickly and economically as well.
Fantastic. Well, Brendan, Chris, thank you for joining us here on the podcast today. Very insightful, very informative. Definitely learned a few things myself today from you guys. So thanks for being on the show. Hopefully we'll have you get on the show again in the future, and we'll get an update on your progress into the rare earth space and how that's going. And until then, for anyone who's listening, if you like the episode, please like and subscribe so you don't miss another show. And we'll catch you guys later.
Thanks.
Thanks.
Thank you.